This is the third part of our video. Just going to give you a couple more examples of the energy approach. In this next problem, we have projectile motion, which we analyzed back in Chapter 2, or I guess Chapter 3. And I don't know, projectile motion was not too hard, but a little bit complicated. But I'm going to show you the energy approach now, and that can be, in some cases, a quick way to get some answers. We're going to ask about the maximum height. So we have an object is shot. So here's ground level. We have an object starting a little bit above the ground, and it's shot at a particular angle, 65 degrees, at a certain speed, 28 meters per second, and of course it's going to follow projectile motion and then land. We want to find the maximum height. So what we can do is use an energy approach, because we can look at the projectile Earth system. That's our system, and gravity is the internal force, which is conservative. And there's no external force while the object is flying, except for air resistance, which again we're going to ignore for the most part. That would change our answer a bit, because that is sucking energy away a little bit. Okay, so we have conservation of mechanical energy. So we can say that the initial kinetic plus potential equals the final kinetic plus potential. Okay, so at the beginning, and so this is the beginning, this is the final. We're ignoring the back half of as the object falls. The final for us in this problem is right at the top. Okay, so initial kinetic energy, so that's just 1/2 mv squared. And this kinetic energy is not directional, it's not a vector, so we just put in the whole 28 meters per second. That's how much speed the object has, and for the purposes of figuring out ki, it doesn't matter which direction it's going. So we'll just put the whole 28 meters per second in. It will also have some potential energy, because it does have an initial height, right? So it'll be mgyi, 0.80 meters above the ground will be the yi. All right. Now, what's happening? What's the energy picture at the end? So at the end, it's going this way, right? It's got all horizontal speed. It stopped going up, but it hasn't started going down yet. So its velocity is entirely horizontal. So it does have speed, so it has its 1/2 m, and then it's just going to be the x component of its speed, which we'll have to figure out. So let me come back to that. But then finally, the potential energy, again gravitational, mgyf. Okay. So yeah, let's figure out this Vx. So for that, we do actually have to go back to the original velocity vector, which is going up at 65 degrees. It was 28 meters per second. And yeah, we can split this up into a horizontal piece and a vertical piece. But we really only want the horizontal piece. That's the one we want. So this guy right here, Vx, is 28 meters per second times the cosine of 65 degrees, which is about 12 meters per second. It's like 11.8. I'll use this isn't a final answer, so I'll use the fuller number in my calculator for when we plug things in later. So 12 meters per second horizontally, and I don't even have to figure out the vertical one, the vertical component. But remember, in projectile motion, horizontal speed stays constant. If you're looking down from the top, you would just see the projectile moving at a constant speed. So this was the initial horizontal speed, but it's actually the final horizontal speed. It's the horizontal speed the whole time. So 12 can go in right here. All right, so we are looking for the maximum height, so we're looking for yf, and I think we have everything else. So I solve, I get mgyf, and I'm just going to subtract this over here. So I'll get 1/2 m and let me just put a I on that V, VI squared minus 1/2 MVX squared, and then plus MGYI. And then, so I can divide by M. Every term had an M in it, so actually I don't need the mass. It turns out that this is independent of the mass. And then I just divide through by G. So YF will be 1 over 2G VI squared minus 1 over 2G VX squared. And then here the G's just cancel, so plus YI. All right, and then you just plug in the numbers. We have everything, and you get 34 meters. So a height of 34 meters. Okay, so yeah, that's a nice way to do it. So you can analyze projectile motion using the energy approach. Okay. I want to include one or two problems that have power involved. Power is the rate of energy transfer, the per second transfer of energy. And let's look at this one. So a motor lifts a load of bricks weighing 800 newtons to a height of 10 meters in 20 seconds. So what's the minimum power of the motor? Okay. So up to a height of 10 meters, the load of bricks goes up. And some device, it's attached to some device, maybe a rope or something that's attached to some motor that's pulling it up. And so what is the power of the motor? So I can, in terms of the energy transfers, there's actually two ways to think about it. I don't have to think of this as a system, although I can. And in fact, let me just show you both, so you realize it can be both, and I don't want you to get confused about which way is the right way. In this case, or often both cases are correct. It's just sometimes one's easier than the other, and in this case, I don't think it matters. So if we just look at the load of bricks itself, not a system of two things, just the bricks itself, right? So, gravity is pulling it down, and the motor, the force from the motor, which probably attached to a rope or something or a chain, so it probably is a tension force, but whatever, we'll just call it the motor's force, is going up. And it starts at rest and it ends at rest, and in the middle we can assume it probably was like you just get it accelerating for just a split second and then get it going at a nice constant speed, and then it can decelerate just for a split second at the end to come to a rest. But for most of the time it's probably going at a constant speed, so the force of the motor has to equal gravity, the force due to gravity, which we already know is 800 newtons. So the motor has to be applying 800 newtons. It might be a little bit more, like I said, because it does have to accelerate it a little bit at first just to get it going. It has to actually be more than gravity at the beginning. And if there's any accelerations and decelerations in between, then yeah, at times the motor might have to go higher than 800 newtons. But, basically 800 newtons is the minimum amount of force that the motor has to apply. Okay, well then, this is happening in, excuse me, not ready for time yet. We have to turn force into energy. So the work done by the motor then is force times distance. So 800 newtons times the 10 meters that it travels. The work done by the motor then is 8,000 joules. And then we can say what the rate is, because that 8,000 joules came over 20 seconds. So, well, so the work divided by the amount of time that elapsed. So 8,000 joules over 20 seconds is, what's that going to be, 400 watts. Okay. Yeah, so the answer is 400 watts. Now, alternatively, you could look at it as the brick earth system, in which case gravity is an internal force. So we don't think of gravity as a force, really, we think of it just as its potential energy. We sort of replace it as a force with its identity as energy. So now it's gravitational potential energy. And we say that this system went from 0 up to 10 meters. So the system, the initial kinetic plus potential energy, right? It has no kinetic energy at the beginning, and it has no potential energy at the beginning. So it starts with 0 joules of mechanical energy. It ends with no kinetic energy, but now it has potential energy. It has mgy, gravitational potential energy, which is mg would be the 800 newtons, right? That's already mg. That's already the weight. That's the force m times g. So we were never given the mass. We could figure it out, but whatever the mass is times g is 800 newtons. So I already have mg, and then times 10 meters is 8,000 joules. So it started with 0 joules. It ended with 8,000 joules. And so the external force of the motor must be doing work and giving it that 8,000 joule increase, right? It went from 0 to 8,000. So the external force is responsible for the change in energy, 8,000 joules of work. And you see, it's the same number, but we kind of got to it in a different way here, just from a different point of view. And then the last step would be the same. You would just divide the 8,000 joules by the 20 seconds and get 400 watts. So you see just two different ways of looking at it. The bricks on their own with two forces acting, or the brick-earth system with one force acting, where instead of gravity being a force as it is up here, it's treated as potential energy for the system here. And again, it's just two different ways of looking at it. So I just wanted to show you that. Okay. Here's another power problem. And again, it deals with gravity. So hydroelectric power. Water flows over Victoria Falls at a rate of this many kilograms every second. So a lot of water going over the fall. And let's say it's 100 meters high. So how much power could you get out of this, right? The idea of water falling down, that's what hydroelectric power is often based on. Right, so the water falls down into, a lake or something, some reservoir, and so as it falls, right, you can have the water pass over some wheel, some turbine, and turn this thing, and that can turn, a generator. It can generate energy, or it can just directly operate a machine, like in the old days. That's how mills used to work. But anyway, you've got some energy that you can do something with at that point. But so how much energy, how much power can you get out of this particular situation, Victoria Falls? Okay, so one new thing about this problem that wasn't in the last problem. In the last problem, it was 10 seconds. The whole process took 10 seconds. This, we don't have a time period. This is just ongoing. Okay, so that's okay. We can just make up a time period. Like we can let's just take 1 second. Okay, and let's just look at what happens over 1 second of this waterfall. So in 1 second of this waterfall, we would have this much water, right? 1.4 times 10 to the 6 kilograms, right? This was the rate per second. So in 1 second, that's how many kilograms of water would go over. So that would be the mass of water going, starting up here and then falling down. So let's concentrate on that amount of water. Okay, so let's do it the system way here. So let's take the water, that amount of water, plus the Earth, so that gravity is now internal. So we can talk about potential gravitational potential energy. Okay. All right. So now the water at the very top, when it starts up at the top, I guess it has a little bit of kinetic energy. The water's moving along, but it doesn't have very much. Let's call that 0. It be a little bit more than 0, but we don't know how much it is. Let's just call it 0. But it certainly has potential energy, and that's the real source of energy here. The fact that it's up high and is going to fall. So we would have mgy. So we've got our m, of course we know g, and we have y is 100 meters. And when you plug that in, you get about 1.4 times 10 to the 9 joules. That is 1.4 gigajoules. So, okay, so a lot of potential energy. All right, so now that's how much energy it has. And if all that energy could be harnessed, could be turned into, could turn this wheel and do some useful work, then that's how much energy we have to work with. And remember, this is every second. So the power is 1.4 gigajoules divided by 1 second, so 1.4 gigawatts. 1.4 gigawatts is the power that Victoria Falls could supply. Again, just to be clear, it doesn't make any difference how much time we look over. If we change this to 10 seconds, then we'd have 10 times as much water, so the potential energy would be 10 times as much. But then we would divide by 10 when we figure out the rate, the power, and we'd be back to where we started. So any delta t that you use, it gets multiplied in here, but it gets divided here anyway. So that's why it really didn't matter, and that's why it's like an ongoing thing. We can figure out the power. We can't say how much energy because it is ongoing. It just is, the energy just keeps racking up for as long as you have this, running. Okay, yeah, so that's it. We didn't have to figure out the energy at the bottom. I mean, it would be the same amount, and we don't really. If we wanted to know how fast the water was falling by the time it got to the bottom, we could do that, right? Because then all this energy would turn into kinetic, and that'd be like kf, and then you could turn that into vf. But we didn't need to do that here. We just had to figure out how much total energy there was at the top, and we know that's how much energy that energy is still there, but by the time it gets to the bottom, and we just turned it into a power. All right. So I will stop this video now.